Okay. So, good morning, everyone. We will continue with the analysis of the transistor. So far we have been looking at the current of single transistor, NMOS and PMOS. Another topic of interest is what is called as the okay. So capacitance, voltage, just like VI characteristics, we generally, when we talk about electrical devices, V is for voltage, I is for current. Like that, here we are going to talk about the capacitance and capacitance with respect to voltage. So this is, the treatment is slightly different. VI characteristics, the current is very important, so we had to look at the derivation and the exact expression for the current. Here we don't care so much about the exact expression. We will just see qualitatively what is the capacitance, sources of capacitance in the structure of a MOS transistor. But this is very important because this determines the speed of the transistor also. We talked about current as determining the speed. Okay, that is a good thing. That is, if the current is high, speed is good. Here, capacitance is a bad thing. So every transistor is associated with a certain amount of capacitance, and one of the properties of capacitance is that it doesn't allow voltage to change instantaneously. That is, there is a capacitor, for example, it has two terminals, right? And each terminal, across the terminal, there will be some voltage. For example, there might be a voltage difference of 2 volts, 3 volts, etc. But one of the properties of the capacitor is that if we are changing one side of the capacitance, the terminal voltage is changing from 2 to 0. Okay, the property is such that the 2 to 0 will take some time, and that time is the main reason why we cannot have instantaneous switching of signals. Anytime we have a transistor level circuit, okay, there will be some time delay, and this time delay is what we see in all our regular day-to-day operation of electronic devices. Your computer is very slow, your mobile phone is very slow. Why is the phone actually slow? If you come down from the software level to the hardware level to actual circuit level, it is because of these capacitances. Every structure, okay, because of the way in which the transistor is built, it will be associated with some capacitances, and these capacitances, they don't allow the terminal voltages. So digital circuits, like we have discussed before, the whole operation of digital circuits is just changing the value of the node voltage. For example, if the first set of inputs come, it might be at some value, for example 0 or 1, and then if the next set of inputs come, it should change from 1 to 0 or 0 to 1. Why that change is not happening quickly is because of the capacitance. Every node will have some capacitance, and first, because we have only transistors, that capacitance should come from the transistor. Nowhere in any digital circuit, okay, the transistor, the capacitance is actually fabricated. No, okay, no, you can have 10,000 gates in your digital circuit, nobody fabricated even one single capacitor. But because of the structure, okay, there will be all these capacitances distributed through the circuit, and these are called as parasitic capacitances. They have no actual functionality, but they are a side effect of the structure of the MOS transistor. So in this class, we will be seeing what is the source of those capacitances. So we are going to divide it into two major components. Okay, so two separate components, and we will discuss each of these separately. And the first is related to the gate terminal. So we have a 3-terminal device, for example, gate, source, drain, and there is a 4th terminal for bulk. So we will see that also in this particular analysis. But mainly, gate capacitance means there are two terminals. So for example, in all the analysis, we will simplify, okay, the capacitances into our parallel plate capacitor. So parallel plate capacitor means there should be two parallel plates. These are the metal parallel plates, and in between there should be a space separated by a insulator. And each of these cases we have to see which two terminals are forming the parallel plate and what is in between that is forming the insulator. And gate capacitance means one of these terminals is always the gate terminal, that is the parallel plates are there, one of the parallel plates is always. So for example, a lot of times we draw it with the gate on top, right? Every time we draw the cross section, the gate is on top. So in gate capacitance, the top terminal is always the gate terminal. The bottom terminal, that depends. So that is what we will see in the first part. The second part is slightly different. Here it is called as diffusion capacitance. And whenever we say diffusion with respect to transistors, MOS transistors, we are talking about the source and drain terminal, because historically, that is in the beginning of the fabrication process, the way in which the source and drain terminals, they were made by a process called as diffusion. That is the fabrication step that created the source and drain terminals was called as diffusion. We saw an example also with the pictures. So that particular name, even though we don't use diffusion anymore, the name continues. It's a historical name. So instead of trying to confuse people with the new name, which is ion implantation. So for example, if you change that, this will be called as ion implantation capacitance, and it doesn't sound so good. So we just continue with the diffusion capacitor. Diffusion, whenever you see diffusion, okay, this means that it is somehow related to the source and the drain terminals of the MOS transistor. So the capacitance associated with those two terminals we will call as a diffusion capacitance. So we'll see each of these separately. Again, the treatment is only qualitative, meaning we just want to see what is the source and understand what are the capacitances associated. There will be no calculation of any values in this unit. Okay. So first let us see the gate capacitance. Okay, so gate capacitance, like we already mentioned, one terminal of this capacitor. Okay, if you simplify it into a parallel plate capacitor, one terminal is always going to be the electrical terminal of the gate, and the other terminal, why we are not fixing the other terminal is because if you remember, we drew the channel configuration for different voltages, right? The channel configuration is different for different terminal voltages. That is why it is called as CV characteristic, right? The gate voltage determines what is the channel configuration. So based on that, the other terminal will vary slightly. So we will see what is that. We will look at the examples. So first, let us consider. Okay, so this is what it will look like when the transistor is off, meaning there is no inversion in the channel region. It is just a p-type substrate through. So in this case, okay, the The gate capacitance itself, what is the value that is determined on the size of the transistor, that is the length and width. We saw the three-dimensional diagram. So the area of the parallel plate capacitor is W into L, and because of that, the total capacitance that is connected to the gate, which we also call sometimes as C0, is C oxide into W into L. So in the first region of operation, when there is no channel or no inversion region being formed, okay, one terminal of the parallel plate capacitor is the gate terminal itself. The other terminal is this full region, okay, that is, this is one parallel, one terminal, this is the other terminal, because this is all connected together. This is one terminal, that is what we have shown here, and the full gate capacitance comes between the gate and the bulk terminal, that is CGB equal to C0 equal to Cox into WL. The other two components, that is CGS equal to CGD equal to, okay, this is the capacitance between the gate and the source, gate and the drain. In this mode of operation, that is when the transistor is off, okay, those two terminals are completely out of the picture. The full gate capacitance comes between the gate and the bulk. So these two, gate source and gate drain, we can just assume that it is 0 in this mode of operation. So this is why we have to divide this gate capacitance into different modes of operation, because the configuration below the gate keeps changing. When I apply one voltage, if the gate is off, if the transistor is off, then it will look like this. If the transistor is on, it will look like this. In on itself, there is linear and saturation. That is why we have divided it into the regions of operation. The first is when the transistor is off. So next, we will consider linear region of operation. That is, VGS is greater than VT, and in addition to that, VGS minus VT is greater than VDS, greater than or equal to. So why this is important is, in this region of operation, the inversion is formed, okay, that much is clear. But in addition to that, if you look at the charge configuration, okay, so if this condition is true, there is a inversion region formed, and the inversion region extends from the source to the drain. So it's a very nice picture, because now directly we can visualize the parallel plates of the capacitor. In this mode of operation, in linear mode of operation, what happens is, this bulk terminal, okay, is completely out of the picture. The parallel plate capacitor, one plate is still the gate, that is always true, but the other plate this time is this. This is basically the inversion region which is connecting the source and the drain terminal, and this whole thing forms the other plate of the capacitor, and the bulk region is completely out of the picture. The bulk is hidden from the capacitor, it is not part of the equation. Now the source is also there, the drain is also there. So how do we say how much is CGS? So first we will write CGB equal to 0. This is not there for this mode of operation because the bulk is out of the picture. Now just to simplify our analysis, we are going to write CGS equal to CGD equal to give half. Okay, what is the difference between source and drain? There is no difference. Both are having the same amount of carriers, both are having the same size, etc., etc. So the capacitance, the gate capacitance, okay, the total value is always the same, that is Cox into WL. This time, how does it get divided between CGB, CGS and CGD? You give half, okay. So this is the whole parallel plate and we are going to divide it equally. CGS equal to CGD equal to C naught by 2 and that is Cox into WL. Cox into WL by 2. So this is for the linear region of operation. And finally, if we extend it to the next natural region of operation, which is saturation, okay, the condition is this, plus this will also change slightly. You can redraw this thing to see if our analysis remains the same. So in this region of operation, we know that the channel does not extend till the source end. So if I can use a different color, okay, so it ends somewhere in between. So again, our analysis has to be changed. So this time, the question is, what are the two plates of my capacitor? If I can decide on that, then we can see how the capacitance gets divided. So this time what happens is, the one plate is the same, that is always the gate terminal. The bulk is out of the picture because there is a partial channel, so we're assuming that it is shielding the bulk region, number one. Number two is this, I have shown it like this, but this is very exaggerated. The channel will not be touching the drain terminal, but it will not be separated by so much, it will be a much smaller value, okay. So the second thing is, this is not touching each other, so CGD is also 0 because the drain and the gate are not in contact with each other because the channel is pinched off. So in this particular mode, we will make a simplifying assumption. Okay, that the gate capacitance is only between the gate terminal and the source terminal, and in addition, by empirical observation, so there is no real theoretical basis for this, we have just assumed over many generations of design that the gate capacitance CGS is approximately equal to 2 by 3 into C naught, that is 2 by 3 Cox into WL. So this is the mode, or this is the capacitance, gate capacitance for the saturation mode. So the gate capacitance, it gets divided between gate source, gate drain, gate bulk, okay, because these are the three regions in which the gate terminal is in contact with. And how it gets divided, the total value always remains the same, Cox into WL, except in this case, of course, we have only 2 by 3 Cox, that is because the parallel plate is not full Cox into WL, but in the other two cases, the full value Cox into WL will get divided between the three, and based on the channel charge configuration, it will get divided into different ways, okay. So this is the first part, gate capacitance. So we will just summarize this with one table. Okay, so we'll just summarize what we have uh, decided on so far in this table. So of CGB is equal to how much? C naught. Okay, because C naught is easier to write, I'll write that only. C naught is nothing but Cox into WL. And in the off mode of operation, the gate bulk is the only capacitance. Gate source, sorry, in the okay, the other two are zero, and the total capacitance, that is the gate capacitance, is the sum of those three. You can just add it here. C naught plus 0 is C naught. In the linear region, the bulk out of the picture, because it is shielded by the channel region, the inversion layer is formed, and these two, we divide them equally between the source and the drain, C naught by 2, C naught by 2, and the total is again C naught if you add all the three. And in the last, in the saturation region, this continues to be at 0. Gate source 2 by 3 C naught, and the gate drain, since the channel region is not touching the drain side, okay, the capacitance cannot be there in the drain side, so that we will assume to be 0. And since the size of the parallel plate capacitor itself has become smaller, because the gate terminal is still Cox WL, but the bottom plate of the parallel plate capacitor, the full length is not L anymore, it is slightly smaller. So because of that, the capacitance itself is reduced 2 by 3 C naught, and the total is just the sum of all those, which is 2 by 3 C naught. So this is the summary of the gate capacitance, the first component of the capacitance that is associated with the structure of the MOS transistor, also called as a parasitic capacitance. Okay, nobody intentionally manufactured any of these capacitances. They are all, so there is no capacitance, there is only a gate terminal, there is a substrate terminal, but it behaves like a capacitance. That is the whole idea of this model. You will not find these capacitances being fabricated anywhere. Okay, it is the gate terminal, the polysilicon, the oxide, the substrate. It is had nothing to do with the capacitor, but the behavior, because it is nature similar to a capacitor, it will have the same effect as a capacitance with these values. Okay, so this is the first component. Next component is our diffusion capacitance. So slightly different analysis from this. Okay, so the first component was called as gate capacitance. So Cg in all of the expressions, all of the terms, Cg was coming. This time we are talking about the diffusion capacitance. So there are two diffusion regions. The source is also a diffusion region. The drain is also a diffusion region. So this is the capacitance not between those two. Okay, there is no direct contact between the source and the drain. Source and the drain separation is somewhat large. So there is no capacitance, for example, called as C source drain capacitance. No, 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 no. It's not there. Okay. The separation is so large that the A epsilon naught by D is very high. So C becomes very small, close to zero, negligible, almost no interaction between the source and drain through the substrate. Okay. So in that case, what is the other terminal? Any capacitance, right? We have seen all these parallel plate capacitors, one plate and the other plate. In this case, I will tell you that one plate is the source terminal. What is the other plate of the parallel plate capacitor? So, for example, what I'm trying to say is, this is CS something, comma, CD something. What is that something? Can you try to guess? These are two capacitances. Both are very similar in nature. Okay, because the source and drain are very similar in nature, the capacitance also associated with them is very similar in nature. That is the, you can call it the source capacitance or the drain capacitance. In general, it is the diffusion capacitance. But what I'm asking here is, what is the other plate of the capacitor? Any capacitance has to have two parallel plates. With one plate, you cannot have a capacitor. So what is the other plate? If you have not guessed by now, that is the bulk terminal. We have the source and the drain, right? And the source and the drain on top, they are covered by the insulation and they have a metal contact. Below is where the capacitance comes into the picture. So we will see in this cross-sectional diagram again, okay, what is the capacitance actually and what is the reason there is this parasitic capacitance. So this time the gate is completely out of the picture. We don't care about the gate terminal. The capacitance is between the okay, this is our fourth terminal or the bulk B or substrate. If you call it substrate S, it will get confusing because already we have a S for source. So that is why generally the B is reserved for the bottom terminal or the bulk terminal. So here, this is the capacitance that we are talking about. So then you might be thinking, okay, you told me that the capacitor should have one parallel plate, another parallel plate, there should be an insulator. I'm not seeing any parallel plates. These are all having some curved shape. So this is a parallel plate capacitor is a simplification. Definitely it is not a parallel plate capacitor because there is no parallel plate itself, right? It is a curved region. And when we say parallel plate capacitor or when we say that the source bulk capacitance, we are simplifying it to a parallel plate capacitor. That is the first thing to remember. Second thing to remember, okay, we simplified it. Where is the insulation? There is a N plus region. It is directly touching the P-type substrate. Where is my insulation? Okay. So for understanding why there is a insulation, definitely. Otherwise, there is no capacitance, right? If I have two parallel plates that are touching each other, then both of them are at the same voltage. I cannot have any capacitance or any property. There is a, unfortunately, it's not a great advantage or anything. It's always a disadvantage to have capacitances because they slow down my circuit. In this case, the reason why we have marked this capacitance is, suppose this is a N plus, which means this is a P-type substrate. Okay, we also discussed this. What is the value of the bulk voltage? That is, for example, if this is an NMOS transistor, this bulk terminal, it is an electrical terminal. So electrical terminal, wherever it is there, okay, we don't have control over it, but that doesn't mean that it is left floating. It will be connected to some particular value. In this case, it will be connected to ground. And now we will see what is the reason it is connected to ground. The reason it is connected to ground, so that even though this doesn't look anything like our PN junction, if you remember from linear integrated circuits, you might have learnt about PN junction. Anytime you have a P-type material and an N-type material that are joined together. So this is interesting. PN junctions are not formed by joining P and N together with Fevicol, right, or with sellotape. We have a silicon substrate. In one part of the substrate, the doping is with P, during which the other part is covered. Then the part which has been doped with P-type, you cover that and then you do N-type doping. So then the same substrate, you have a P-N junction. So it's not that somebody makes P, somebody makes N, they bring it together in their car and join it together and make P-N junction. It is from the same substrate, just with the control of doping using our mask and photolithography, we make this P-N junction. So in this case, we didn't make the P-N junction, we put the n-type doping on top of the p-type substrate, but still it is a region where n and p are touching each other, so automatically it is a p-n junction. So if you want, I can draw it like that also. Right, this is my PN junction. I'm only looking at the junction part here, and I'm trying to explain why there is a capacitance. So we understand that there are two parallel plates, but also because of this particular connection, okay, this PN junction. So if you want, I can draw the it's a little lower. PN junction, and I have connected this to a negative terminal. Here also it is the same, because in my condition 0 is the most negative value I can get. So I have actually connected it. So this and this is the same. So now you have to remember what happens when you reverse bias a PN junction. The effect is, yes, you cannot have current flow, but also at the junction you will have something called as a depletion region. Depletion region is where there are no mobile carriers, and because there are no mobile carriers, okay, it acts as a insulator. So whenever we have two parallel plates separated by an insulator, it's a capacitor. Here also the same thing. We have two parallel plates, and both the parallel plates are separated by a, this is the depletion region, okay, and because of this biasing, this depletion region will always be there. It might increase slightly or decrease slightly in terms of the voltage applied to this terminal, but it will always be there. It will never disappear. This connection is such that this junction can never be forward biased. When will the depletion region disappear? It will disappear only if the junction is forward biased. That can never happen, right? Because we have only two voltages, VDD and 0, and this is at 0. At most this can go to 0. So 0 0 means still it will be having a small depletion region, and this depletion region is the insulator. And whenever we have an insulator and two parallel plates, we have a capacitor. So that is the source of the capacitance for the diffusion capacitance, and identical, whatever happens on this side, same thing will happen on that side also. So I'll just write it down here. CSD, sorry, not CSD, CSD and CDD are okay. So this is the reason why there is a capacitance, because that terminal is permanently connected to ground and it will be permanently reverse biased. So this basically is the source bulk and drain bulk, and we don't care about the expression. It is just remember that there is a capacitance associated with the diffusion terminals. So together we have talked about the overall picture. So let us put it all together and draw this very important diagram. That is the diagram of all the capacitances associated with a single transistor. That is, I have one transistor. It might be NMOS, it might be PMOS, and in NMOS and PMOS, the nature of the capacitances are all identical. Okay, there is no difference at all. Only thing is the values depend on the size of the transistor, but the sources and the nature of the capacitances are identical. So one diagram I want to draw, which is a very important diagram, especially for the later units when we are looking more into the delay of a transistor, the summary of MOS capacitances. Okay, so first I will draw the MOS transistor. It may be NMOS, it may be PMOS, doesn't matter. Okay, and we are not showing the fourth terminal, but it is there, and a lot of these capacitances, the fourth terminal will come into the picture, but just for simplicity's sake, we will not show that. So what is the most important thing to remember for the future units and in general also? Every transistor, okay, is associated with three capacitances. Okay, what are the three capacitances? The first capacitance CG. Okay, we don't care about the other terminal. The gate capacitance is there, it will have a value. The other terminal might be the source, it might be the bulk, it might be the drain, it might be anything, but there will be some value, right? So this is one capacitance. What is the other capacitance? D, capital D, small, you can use uniform this thing, just to be uniform, I'm capital D. The other capacitance of this is a NMOS transistor, right? So other capacitance, one terminal is the drain terminal. The other terminal of this capacitance is the bulk terminal, and if you remember, NMOS bulk is connected to ground. So this is the second capacitance associated with the transistor. Third capacitance, that is simple, once we have CSD, that is the source bulk capacitance. So this diagram is very important. Okay, every MOS transistor is associated with three terminal capacitances. One is associated with the gate terminal, and the other two are associated with the diffusion terminal, CSB and CDD. And the gate terminal, the other capacitance is depending on the region. We don't have to worry about all that. We have done the detailed analysis. We only know that some particular value will be there at the gate terminal. So this is for a NMOS transistor. I will also draw it for a PMOS transistor. Okay, PMOS transistor, everything is same except we have the bubble. So the first capacitance is identical, CG. Okay, and the second and third are also almost identical. Now one question I want to ask is, for PMOS transistor, the diffusion capacitances, which I have half drawn there, how do I complete that diagram? This diagram is complete. I have shown the other terminal also where it is connected. In this one, if I want to complete this, how should I complete this? That is here. Where is the bulk terminal of the PMOS transistor connected? It is always connected to VDD or power supply, and that is why the diffusion capacitances or the diffusion junction, PN junctions, are always reverse biased, and because of that it is connected to VDD. So up means it's connected to power supply, down arrow means it's connected to ground. So this picture is very important. Every transistor, NMOS or PMOS, 3 capacitances, gate, source bulk, drain bulk, and the other terminal depends on the type of transistor. It might be ground, it might be VDD. Okay, so this is a quick summary. Summary spelling is wrong, but still the summary is correct. Quick summary of the sources of the capacitances associated with the MOS transistor, and we don't have to worry about the calculation values, etc. These diagrams are also very important because in the fourth unit, we will be using these diagrams a lot to calculate the delay of a circuit. Okay. So the next topic is coming back to the VI characteristics. Okay. So non-ideal. Okay, what is the meaning of this non-ideal? So maybe directly because of that we can determine that the VI characteristics that we derived and the equation that we are using is called as the ideal VI characteristic, and then this is called as the non-ideal because we also mentioned this briefly, but if we use the equations and calculate the current, we might be around 80% close to the actual value given by a simulation. Now, simulation doesn't mean that the device is actually there. Simulation just uses some mathematical models for the transistor and uses some equations, maybe some differential equation, and gives you the current. So if you use a good simulator, you will see that the value is different from ours that we have calculated using our VI equations by around say 20% or so. Doesn't mean that the equations are wrong. Okay, for hand calculations we can only use that much. We cannot every time somebody asks us to do something, we cannot go to the simulator and create the circuit and do the simulation. That doesn't mean that we have to do that every time. The hand calculation, our accuracy is okay, but suddenly if I see a VI characteristic and it will look very different from what we have been drawing, we have to know what are the reasons. Okay, what are the main, there are many reasons. Okay, we are just going to look at a few of the reasons why the real current is differing from what we have calculated. So the first one, and in my opinion the most important one, is called as channel length modulation. Okay, channel length and this is very common. This is just so common that the equation itself we have to slightly modify. If we are calculating the current, there is a slight modification for the equation. But what is the meaning of this channel length modulation? So first question, what is this channel length? Okay, what they mean by this channel length is the length of the transistor. That is, we have a L, right? That is the distance between the source and the drain. That particular distance is a very important terminology in VLSI design. It's also called technology, etc., etc., etc. But that is what is the channel length. Now, modulation generally means changing. So channel length modulation is an effect where the value doesn't stay constant all the time, and you might think, but that transistor is fabricated. How is suddenly the source and drain, how are they coming closer to each other, right? That is what it means when the channel length is changing. The source and drain separation is called as channel length. If the source and drain separation is changing, then only the length can change. Okay, that is where there is a slightly different phenomenon, and for that we have to remember something called as pinch off. Pinch off means that the channel doesn't extend all the way up to the drain side. Before that only it gets pinched off, and that is where the size of the channel, okay, keeps changing. It is not the full L anymore. It is slightly lesser than L. And as we saw in some of the diagrams, okay, if I increase my VDS, the channel pinch off comes closer to the source, which means the effective channel length, okay, is even lesser now. So that is why the current doesn't stay the same as predicted by our equation. So I'll show one example of the current in a sample graph. So this is my current IDS, and this is VDS. Okay, so maybe I will use two colors. So with white, I will show the old curves. Okay, this was the one we drew earlier also, but in actual this thing, it will not be like this. Okay, so the yellow, this is the, I don't want to call it actual, but I don't have any better name. And this is the ideal case. And the yellow one, okay, we see that the current is not staying the same. It is actually increasing when we are in the saturation region. That is the first thing, because if you remember, we drew this diagram where in the ideal case, at least up to certain point, okay, the current keeps changing with the VDS, but after a certain point the current stays the same. So that region is called as saturation. But in the real case, even in saturation region, the current is slowly increasing. What is the reason for that? The reason for that is our pinch off phenomenon. So pinch off phenomenon, so I've just magnified this. Okay, let's say that A, VDS equal to 2 volts, okay, and is greater than VGS minus VT. So I will draw VGS minus VT. Let's say that this is approximately 1.5 volts. Okay, so then my this is the effective channel length. The channel doesn't extend from the source to the drain. It is slightly smaller, and because of that, we see that the current is more. Now, why the current is more? That is because the L parameter in our current equation, okay, L is in the denominator. So if the L is reduced, then current increases. It's inversely proportional to current. So that is why we see that the current is increasing. Second thing is, why does it keep increasing? Right? That is because if I go further higher, okay, that is if I go from B case to now, if I draw this, I've magnified it to a large extent. It will not reduce by this much. But what I'm trying to say is this channel length is no longer a constant in the saturation region, especially as the VDS keeps increasing. Okay, the effective channel length keeps reducing, and because the effective channel length keeps reducing, the current keeps increasing. That is what we see in the yellow curve. The current doesn't stay the same. As we keep increasing VDS, the current also keeps increasing, and this current won't increase forever because VDS has an upper limit. VDS upper limit is power supply voltage, maybe 2 volts, maybe 3.3 volts, but it will increase up to a certain point. But the most important thing is the current doesn't stay the same. It increases along with VDS up to a certain point. Okay, that is the first non-ideal VI characteristic, and the actual amount, okay, by which it increases is given by a parameter called as, I'll remove this part. Channel length modulation parameter lambda. Okay, this is the something that is given by experimental observation. That is, suppose somebody is making a transistor in 180 nanometer technology, and they want to provide a model to the simulator, right? So you can't just provide a model by doing theoretical calculations. They will have an actual device, okay, and they will put that in a test bench, and they will give a voltage, they will see the current, and from this curve, okay, they will measure the slope. That slope is given by this value lambda, which means that when I'm calculating the current, therefore IDS equal to mu Cox by 2 into W by L into VGS minus VT the whole squared into 1 plus, okay, this is the new equation for current because of channel length modulation. And if you make a simplifying assumption, okay, this lambda, a sample value, for example, might be